If you were asked to describe Jupiter, you'd probably picture that classic school textbook image. A massive striped sphere with a red spot, drifting steadily and majestically through the black void. For a long time, scientists thought of it as a nearly frozen world, an ancient giant simply holding onto the leftover material from the solar system's birth. But here's the catch. That image is almost entirely wrong. Jupiter is anything but calm or frozen. If you dig a little deeper, the familiar picture starts to fall apart. Let's start with mass. Jupiter's mass exceeds the combined mass of all the other planets in the solar system. Not just any single planet, but all of them together. Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune. Put them on one side of the scale, and Jupiter still outweighs them. It's not just the biggest planet, it's the gravitational anchor of the entire system. We think we revolve around the Sun, but technically the whole system orbits a point located just outside the Sun itself, and that's all because of Jupiter. Here's the strange part. Despite its monstrous mass, Jupiter spins faster than any other planet in the system. It completes a full rotation in less than 10 hours. 10 hours? On Earth, a workday barely ends, and on Jupiter, a full day has already passed. This incredible speed flattens the planet at the poles and bulges it at the equator, turning it into a giant, boiling cauldron. And that's not all. Surrounding the planet lies something invisible yet immense, its magnetic field. It's so powerful and vast that if we could see it with the naked eye, it would cover more space in the night sky than a full moon. Imagine looking up and seeing two giant disks, one bright, the other ghostly. But the biggest puzzle, the one that forced scientists to rethink everything they knew, is the heat. Jupiter sits 5 times farther from the Sun than Earth does. It receives only a tiny fraction of the Sun's energy, yet it radiates more energy into space than it takes in from that distant star. It's as if it hides its own internal heat source. This isn't just a planet reflecting sunlight, it's a world that warms itself. It follows its own internal rules and not the ones set by the Sun. A planet without a solid surface might just be the cradle of life. Today, we'll trace the entire story of Jupiter, from its birth, which shaped Earth's fate, to the probe's plunge into its bottomless atmosphere that upended all our theories. We'll witness how the giant's internal fire fuels a whole system of worlds, including moons with hidden oceans beneath their ice. And we'll try to understand why this planet ended up far from where it was supposed to form. So, how did this giant, which follows its own rules rather than the Sun's, come to be? Its story began in chaos, a story that set the destiny of the entire solar system, including our own planet. 4.5 billion years ago, there were no planets, no orbits, no familiar order. Around the young, raging sun, a massive, churning disk of gas and dust swirled, the leftover debris from its own birth. A cosmic fog, pure chaos. Billions of icy and rocky chunks collided, stuck together, shattered, and clumped again at random. It was a brutal game of survival. The winner? The one that grew the fastest. Jupiter grew first. It became the gravitational anchor in this chaos, pulling in gas and dust greedily while everything else was still struggling to form something solid. The firstborn of the solar system. Composed almost entirely of hydrogen and helium, just like the Sun, this object was long mistaken for a failed star. It was as if our solar system had a second dim lantern. And in fact, it came just short. If it had been several times more massive, the pressure in its core would have ignited nuclear fusion. But it stopped right at the threshold. It remained a planet, yet its birth was a fiery one. As it contracted and gathered mass, it released an immense amount of heat. Not from nuclear fusion, but from gravity. Part of that original energy still lingers deep within its core. This explains the mystery from the previous chapter. It emits more energy than it receives from the Sun because it is still cooling down from its turbulent birth. But the most important part is this. By arriving so early, Jupiter didn't just take a spot. It started setting the rules for everyone else. Scientists believe that without Jupiter's early presence, the solar system would look completely different. Its gravity acted like a cosmic traffic controller, clearing certain orbits by flinging leftover debris out of the system, while stabilizing others to create safe zones where new worlds could quietly take shape. Without Jupiter, the inner planets might never have found stable orbits, including Earth. Our calm blue planet is, in a way, a side effect of its older brother's timely arrival. Jupiter is the architect of our home. At first, the story seems straightforward and logical. It was born first, gathered gas, and brought order. But in 1995, this neat picture shattered. A special probe detached from the Galileo spacecraft plunged into the giant planet's atmosphere in a final, fatal descent. It transmitted data for just 57 minutes, until the crushing pressure crushed it. Yet in that brief window, it sent back a bombshell. The probe detected unusually high levels of heavy elements: argon, krypton, and xenon. On the surface, it's just chemistry. But for astronomers, it was a shock. Here's the problem. These substances only condense, changing from gas into solid particles at extremely low temperatures, much colder than those found in Jupiter's current orbit. Finding them there is like spotting an iceberg in the Sahara. It simply couldn't have formed there. This clue pointed straight to one of two possibilities. Either Jupiter was born far from where we see it today, out in the distant, icy edges of the solar system, and then migrated closer to the Sun, or it somehow acted like a giant vacuum, sweeping up this material from the coldest reaches. What seemed like a straightforward origin story turned into a mystery. So, this giant planet formed early on, shaped everything around us, and may have wandered through the solar system. But what does it look like now? If we could journey down to its core, what would we find? The answer is both simple and utterly mind-boggling. So, what would we actually see if we traveled to the center of Jupiter? The answer is surprisingly simple, and a bit unsettling: nothing. Just emptiness. Jupiter doesn't have a surface like we understand it on Earth or even Mars. There's no clear boundary where the atmosphere ends and the planet begins. Those stunning bands and swirling storms we see in photos? They're just the planet's thin upper layer of ammonia and hydrogen sulfide clouds. If you tried to fall through them, you'd fall forever. Jupiter hides no solid rocky crust beneath those clouds. Instead, you would sink deeper and deeper into an endless ocean of gas, growing denser and denser the farther you descend. At first, it would feel like flying through a fog, but with every mile, the pressure would climb at a terrifying rate, and the temperature would rise. Soon, the atmosphere would thicken, first becoming as dense as water, then as heavy as molten metal. At a certain point, hydrogen, the planet's main ingredient, stops behaving like a typical gas. It compresses, condenses, and shifts into a state scientists first call liquid, then metallic. This isn't gas or liquid anymore, it's something entirely different. An exotic substance that exists under millions of atmospheres of pressure. You wouldn't just fall to the bottom, you would become part of it. Where does all that energy come from in this bottomless abyss? Why does a planet so far from the sun bubble and churn like a boiling cauldron? Here lies the answer to the mystery we left hanging in the first chapter. Jupiter radiates into space almost twice the energy it receives from the distant sun. This happens because deep inside, it constantly releases heat trapped since the planet first took shape. Scientists call this process gravitational contraction, and it's still happening right now. Jupiter slowly compresses under its own immense gravity, and this compression generates an enormous amount of heat. It's the planet's internal engine. On Earth, the sun drives the weather. But on Jupiter, it's the opposite. The climate is powered from within, while sunlight plays only a minor role. Deep inside Jupiter, intense heat drives powerful currents that surge upward from its core. Now add another crucial factor. Jupiter completes one full rotation in less than 10 hours, faster than any other planet in the solar system. This rapid spin twists those rising energy currents into massive, stable structures. That's why storms and vortices on Jupiter don't break apart like Earth's hurricanes. Instead, they can last for decades, even centuries. They don't feed on ocean warmth, but on the planet's own endless energy. The most famous of these endless storms is the Great Red Spot. It's so vast that at different times it could hold not just one, but several Earth-sized planets inside it. And it's incredibly old. Astronomers have known about the Great Red Spot since the 17th century. Think about that. When they first spotted it through a telescope, steam engines hadn't even been invented yet. Entire empires rose and fell, while this storm has raged on Jupiter for at least several hundred years, barely changing. For a long time, scientists assumed it was just a massive weather system. A long-lasting one, but still just weather. Another mystery we could only observe from the outside. But we were wrong. Everything changed when the Juno spacecraft arrived at the planet. Its instruments pierced through the thick clouds. What they found turned every assumption upside down. The spot wasn't just a surface ripple, it extended hundreds of miles deep into the atmosphere. This wasn't simply a hurricane, it was a colossal three-dimensional vortex, rooted deep within the planet's interior. But the biggest revelation came when Juno measured the temperature at its base. It turned out to be significantly warmer than the surrounding layers. That meant this vortex connects to powerful flows of energy and matter from within. It literally sucks heat from Jupiter's core. That's why it survives for so long. It's not just a storm. It's the visible exhaust of the planet's internal engine. And this engine doesn't only create visible storms. Far beneath the surface, where hydrogen turns metallic, it generates something invisible, but so powerful that its influence stretches well beyond Saturn's orbit. This invisible force is his empire. Jupiter stands as the most powerful magnetic object in the entire solar system. Not just a planet, but an object of immense magnetic strength. Its magnetic field is 20,000 times stronger than Earth's. If we could see it with the naked eye, it would span an area in the night sky several times larger than the full moon. Imagine a giant, shimmering bubble. Inside it, Earth and all its moons would be nothing more than tiny specks. This zone of influence is called the magnetosphere, and it's colossal. Jupiter's magnetosphere stretches millions of miles, with a tail pushed by the solar wind that extends far beyond Saturn's orbit. Jupiter literally holds its neighboring giant planet in the grasp of its invisible power. But how can a gas giant even act like a magnet? On Earth, the magnetic field comes from its molten iron core. Jupiter doesn't have a core like that. The answer lies much deeper, in that exotic layer we already mentioned. Deep within Jupiter, hydrogen faces such immense pressure that it turns into a metallic form. This metallic hydrogen conducts electricity just like a copper wire. Now add the planet's rapid spin to the mix. Jupiter's furious rotation sets this conducting material in motion, creating a colossal dynamo. Essentially, at Jupiter's core, there's a power plant the size of a planet, and it never stops running. But this invisible empire isn't empty space. It actively interacts with everything that enters it. The most dramatic example is the dance between Jupiter and its closest major moon, Io. Io is a volcanic world, the most geologically active body in the entire solar system. Its surface constantly erupts, spewing tons of material into space. Sulfur, oxygen, everything in between. These particles don't drift off into the void. Instead, Jupiter's magnetic field grabs them immediately. Jupiter acts like a cosmic vacuum cleaner, pulling in everything its moon ejects and spinning it around itself. This process creates a dense plasma torus, a massive invisible ring of superheated gas that rotates with the planet. Io constantly feeds this structure, while Jupiter's immense power holds it in place. This isn't just a planet and its moon anymore. They form a single, complex electromagnetic system, where one directly shapes the environment around the other. Inside this torus, radiation levels soar so high they can disable the electronics of any spacecraft daring enough to linger too long. For a long time, scientists considered the dynamo model to be elegant and complete. But, as often happens, reality proved more complicated. When the Juno mission arrived at the planet equipped with the latest instruments, it peered straight into the heart of this invisible empire. And here's what it found. Jupiter's magnetic field turned out to be far from uniform. It showed a clear asymmetry, especially between the northern and southern hemispheres. In some areas, the field was much stronger than the models predicted. In others, noticeably weaker. This tells us that the internal dynamo mechanism is far more complex than we thought. It's as if something inside the planet distorts the field, creating strange, abnormal zones. Once again, we face a mystery hidden deep beneath the clouds. For centuries, we could only guess at these processes. But at the end of the 20th century, our first permanent envoy arrived at Jupiter. A spacecraft designed not just to fly by, but to stay for the long haul. And its discoveries changed everything. This probe was called Galileo, but it didn't just fly past like the missions before it. Galileo became the first spacecraft to enter orbit around Jupiter and begin a long, systematic study of the planet and its moons. It was supposed to be our eyes and ears in this distant system. Yet even its creators couldn't have imagined the cosmic spectacle it would witness on its approach. In 1994, while Galileo was still en route to Jupiter, the unimaginable happened. Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity into more than 20 fragments, slammed into the planet. For the first time in human history, we watched live as two massive bodies in our solar system collided. It wasn't just a flash of light, it was a chain of disasters unfolding over several days. Fragments of the comet, some spanning several kilometers, slammed into Jupiter's atmosphere one after another. Each impact unleashed energy equal to hundreds of millions of nuclear explosions. Towering columns of superheated gas shot thousands of kilometers above the clouds. Dark scars, as large as Earth itself, marked each strike. The spacecraft Galileo, positioned perfectly, witnessed what Earth-based telescopes could not, the very moments of impact. A cosmic catastrophe that might have taken millions of years to occur unfolded right before our eyes. But that was just the beginning. The main act of this drama was yet to come. In 1995, upon arrival, Galileo carried out its most daring mission. It released a probe into the planet's atmosphere, a small titanium capsule tasked with something no one had ever attempted before. It dove into Jupiter's depths, sending back data straight from the heart of the storm. Scientists had waited decades for this moment. They were confident the probe would confirm their theories. What they most hoped to find was water. Lots of it. According to every model, Jupiter should have been rich in oxygen, and therefore packed with water vapor. This element was the cornerstone for all theories about how planets form. The probe entered the atmosphere at nearly 50 kilometers per second. Its heat shield surged to temperatures hotter than the surface of the sun. The forces crushing it were immense. But it survived. And it started sending data back. For 58 minutes, it plunged deeper, measuring pressure, temperature, and chemical makeup. Then, crushed by overwhelming pressure, it fell silent forever. When scientists on Earth received and decoded its final message, silence fell over the Mission Control Center. The data shocked everyone. The probe passed through a dry layer of the atmosphere where water was far scarcer than anyone expected. Almost none at all. This wasn't just a surprise, it tore apart the entire theory. Without water, our understanding of how and where Jupiter was born was fundamentally wrong. It hit the scientific community like a thunderclap. The mission's main objective seemed to have failed. But hidden within this apparent failure was one of the greatest discoveries. Yes, there wasn't much water. Yet the Galileo probe detected unusually high concentrations of argon, krypton, xenon, and other inert gases. These are chemical ghosts. They rarely react with anything, so their presence serves as a direct fingerprint of the primordial material from which the planet formed. Here's the strange part. For Jupiter to capture so many of these gases, it must have formed in a place far, far colder than its current orbit. The only way to trap them was by freezing them into icy clumps, and that required temperatures of minus 170 degrees Celsius. The Galileo mission shattered the image of Jupiter as a simple, familiar giant. It couldn't have formed where we see it today. Instead, it was born far out on the cold outskirts of the solar system. Then, for reasons we still don't fully understand, it migrated closer to the sun, clearing and reshaping everything in its path. The failed search for water sparked a revolution in how we understand the entire structure of the solar system. But that was just the beginning. While scientists wrestled with the mysteries of Jupiter's atmosphere, the Galileo orbiter spent years circling the planet. And it sparked another revolution, this time in the study of Jupiter's moons. This mission revealed that Io is the most volcanically active body in the solar system. It uncovered a vast ocean of liquid water beneath Europa's icy surface. And it discovered that Ganymede, the largest moon, has its own magnetic field. Galileo revealed that the most fascinating worlds in Jupiter's system might not be on the planet itself, but orbiting nearby. It unveiled an entire miniature solar system, where each moon shines as a unique gem. This miniature solar system turned out to be far stranger and more diverse than anyone imagined. Jupiter's moons aren't just chunks of rock and ice. They are fully fledged worlds, each with its own personality, unique geology, and distinct fate. Traveling among them is like leaping from one marvel to the next. Let's start with the moon closest to Jupiter. Its name is Io, and it's literally a vision of hell. A world painted in yellow, red, and black sulfur, a landscape of relentless volcanic eruptions. Io holds the title of the most volcanically active body in the entire solar system. Hundreds of volcanoes shape its surface, some shooting molten plumes hundreds of miles into space. But if we move just a bit farther to the next moon, we leave this inferno behind. There, Europa awaits. A cold, quiet, almost perfectly smooth ice ball. Its surface is marked only by thin, long cracks, as if giant scars were carved across the ice. Beneath this icy shell lies both Jupiter's greatest secret and its biggest hope. Data from the Galileo spacecraft left no doubt. Beneath Europa's smooth surface hides a vast ocean of liquid water. Not just a lake or a sea, a full ocean encasing the entire moon's core. Early estimates suggest its volume might surpass all of Earth's oceans combined. Think about that. On a tiny moon, far from the sun, in endless darkness, there's more water than on our own planet. A warm, salty ocean, shielded from cosmic radiation by a thick layer of ice. And it has existed there for billions of years. Let's keep going. Next up is Ganymede, the largest moon of Jupiter and, in fact, the biggest moon in the entire solar system. It's even bigger than the planet Mercury. But what sets Ganymede apart is its own magnetic field. This isn't just a moon. It's a planet caught in the grip of another planet's gravity. And the farthest of this group is Callisto, a world frozen in time. Its surface is densely pockmarked with craters and has barely changed for billions of years. A cosmic relic, a living archive carrying scars from the very earliest days of the solar system. Here's the question that naturally arises. How can a single system host a fiery hell, an icy ocean world, a moon that's almost a planet, and an ancient cosmic artifact all at once? The source of their energy isn't the sun, it's simply too far away. The real power comes from Jupiter itself, more precisely from its gravity. These moons don't just orbit the giant planet, they constantly interact in a perfect gravitational dance. This dance slightly stretches their orbits, which in turn makes the moons flex and relax under tidal forces. Imagine bending a wire back and forth quickly. It heats up. The same thing happens here. Tidal forces heat their interiors, fuel volcanic eruptions, drive ocean currents, and keep geological activity alive. Jupiter's gravity acts like a perpetual engine, never letting its moons cool down. The Galileo mission gave us these worlds, but it also revealed the limits of our knowledge. We caught a glimpse of the king's entourage, yet the king himself remained a mystery. Even Galileo couldn't peer beneath the planet's clouds or unlock the secrets of its core. To do that, we needed a new, more advanced explorer, one tough enough to survive the deadliest radiation belts and look straight into the giant's heart. This spacecraft earned the nickname Juno. But its mission was unlike anything attempted before. Previous probes studied Jupiter from the equator, keeping a safe distance. Juno had to achieve the impossible, stare the planet straight in the face. To do that, engineers designed a nearly suicidal plan. The spacecraft follows an incredibly stretched orbit, spending weeks far from Jupiter in relative safety. Then, once every few weeks, it makes a lightning-fast dash, zooming over the planet's cloud tops, slicing right through the deadly radiation belts, gathering data in just a few hours. It's like a diver plunging to the bottom of the Mariana Trench for only seconds before the crushing pressure would overwhelm them. Every flyby is a dance with death. But this boldness made Juno the first spacecraft to systematically explore Jupiter from a polar orbit. And what it saw there shattered every scientific prediction. We're used to seeing Jupiter as a striped, relatively ordered world from the equator. You might expect that at the poles, where the planet's furious spin hits hardest, there would be total, uncontrollable chaos. But the reality is far stranger, and far more beautiful. Instead of a chaotic storm mess, scientists found organized structures, giant cyclones arranged in stable, geometric patterns. At the North Pole, 8 massive whirlwinds, each the size of a country, circle a central storm. At the South Pole, 5 equally huge cyclones rotate around their own leader. They don't merge or drift apart. They hold formation, like parts of a colossal living machine. Nothing like this exists on any other planet in our solar system. Why does nature favor geometry on a planetary scale? We still don't have an answer. But the biggest surprise didn't come from the outside. It came from within. For decades, scientists pictured the gas giant with a simple structure: a dense, compact core of rock and ice at the center, surrounded by a vast ocean of metallic hydrogen and a thick atmosphere, like the pit inside a peach. The Juno spacecraft, probing hundreds of miles into Jupiter's atmosphere with its instruments, was supposed to confirm the size of that pit, but everything fell apart at that point. It turns out Jupiter probably doesn't have a solid, clearly defined core like rocky planets do. Instead, deep inside, there may be a fuzzy, extended region, a blend of heavy elements mixed with hydrogen and helium. The core isn't solid. It seems to dissolve into the planet's interior, stretching out to nearly half its radius. This isn't just a simple detail. It completely rewrites the story of Jupiter's birth. Such a blurry core could only form in one way. Early in the solar system's history, the newborn Jupiter collided with another protoplanet about 10 times the size of Earth. The impact was so powerful it shattered Jupiter's original core and mixed it into the surrounding gas. Remember the mystery of the excess heavy elements we mentioned at the start? This might be the answer. Jupiter didn't just gather them from the nebula, it swallowed the heart of another world. The deeper Juno probes, the more complex the picture becomes. Jupiter's magnetic field isn't just incredibly strong, it's surprisingly uneven. It forms closer to the surface than we expected, with strange hotspots, especially in the northern hemisphere. The ammonia and water in the atmosphere don't spread out evenly either. This points to an incredibly complex weather system, stretching thousands of miles below the clouds. Jupiter isn't a tidy onion with neat layers, it's more like a boiling cauldron, where everything mixes far more wildly than we ever imagined. Juno has revealed that the deeper we look, the less we understand Jupiter. But all these discoveries, internal heat, tidal forces on its moons, complex chemistry, lead us to one big question, one that changes everything. And the most important question that all these discoveries have brought us to isn't about Jupiter itself. It's about us. It's about life. We've always seen Jupiter as a hostile, raging giant, a place where life simply can't exist. And that's true. Jupiter itself is unlikely to support life, but it plays a crucial role as an energetic and gravitational anchor, shaping the conditions for potentially habitable worlds around it. Jupiter isn't a home. It's an engine that powers and warms the homes nearby. In that sense, Jupiter isn't a world for living beings. It's a guardian world. Scientists focus their attention mainly on Europa. Beneath its icy shell, tens of kilometers thick, lies a vast ocean of liquid water. We've talked about this before, but now, understanding the tidal forces, we see where all that heat comes from in this frozen world. Jupiter's gravity constantly squeezes and stretches Europa's core, heating it from within, much like bending a wire over and over again. Try it yourself right now. The metal warms up. That's exactly how it works here. This heat keeps the water liquid for billions of years. But life needs more than just water. It requires energy and chemistry, and this is where things get truly strange. Scientists believe that at the bottom of this ocean, hydrothermal vents could exist, underwater volcanoes similar to those on Earth. There, in complete darkness and under pressure hundreds of times greater than Earth's atmosphere, hot mineral-rich streams gush from cracks in the rocky floor. On Earth, these spots rank among the most likely cradles of life. They form entire oases that thrive without a single ray of sunlight, drawing energy solely from the planet's chemical processes. If life exists on Europa, this is probably what it looks like. This is exactly why the Jupiter system changed how we think about habitability. For decades, astronomers looked for life in what they called the Goldilocks zone, the sweet spot around a star where it's not too hot and not too cold, allowing liquid water to exist on a planet's surface. But Jupiter and its moons showed that rule isn't absolute. Liquid water can exist far from the sun if there's another energy source, the gravity of a giant planet. Sunlight is no longer the only condition for life. Now, let's look at the flip side of this discovery. If subsurface oceans can exist on the moons of gas giants, it means there could be far more potentially habitable worlds than we ever imagined. Almost every star has its own gas giants, and many of those giants have icy moons orbiting them. This doesn't just increase the number of possible cradles for life by a few times, it multiplies it by orders of magnitude. Billions of new opportunities for even the simplest life forms to have taken root somewhere else in our galaxy. And so, we return to the beginning, to the giant that came first, shaped the fate of the entire system, shielded Earth from comets, and still holds the primordial heat of its birth. Now, we understand that its story is more than just the biography of the largest planet. It's a story about how unexpected pockets of life might emerge in the universe. In the coming decades, new missions will head to Europa and Ganymede, aiming to peer beneath their icy crust. If they discover even the faintest traces of simple microorganisms, it will rank as one of the greatest discoveries in history. Should that happen, Jupiter will forever be known not only as the largest planet in the solar system, but also as a key player in answering humanity's oldest question: are we alone in the universe?